Hi and welcome back to our lecture series in mathematics. I am Rajesh from Cloud Tutors. The last chapter we dealt with was integration, and there, of course, what I discussed in detail was the different techniques of integration, but fundamentally, you also learned what the graphical representation or meaning of integration is. So, integration can be used to calculate the area under a curve. So that was the graphical understanding of the process of integration. Now we will take that a step further and see where integration can be applied. Now integration as a mathematical tool can be applied in numerous situations, and it is important to realize the vast number of applications that exist for integration. So we will touch on some of these applications as part of the next chapter titled Applications of Integration. So before we start talking about specific applications of integration, right, let's start by reviewing what I told you in the earlier chapter, the concept of area under a curve and how we can find the area under a curve using integration. And then we will talk about specific areas in which integration can be applied. This is not an exhaustive and complete list by any means, but these are some examples where integration can be applied. The first is to find the area between two curves. Then it is to find, so this would be a two-dimensional kind of problem, area between two curves in the xy plane. This would be a three-dimensional kind of problem where we find the surface area or volumes of solids using integration. So this would be in the in three dimensions, and then we will see how we can apply integration to situations like kinematics, bodies which are moving. There may be displacement, acceleration, force being applied, work being done, and problems like that we can solve using integration. So these are the specific areas in which we will study how integration can be applied. So before we jump into these areas, let's take a look at what definite integrals mean. And this was one of the topics discussed as part of the previous chapter. And this is fundamental to our understanding of applications of integration. So let's spend a minute or two talking about definite integrals. So if you have an integral of a function small f of x given by f of x, it essentially means that if you are integrating between the limits x is equal to a to x is equal to b, then this becomes f of b minus f of a. So this is the mathematical process. So what does it mean in graphical terms? Well, this is what it means. If you have a curve which is represented by y is equal to f of x, and you want to find the area under the curve. Now this is the curve here, and you want to find the area under the curve. So what are the four boundaries of this curve? Well, below here you have the x-axis itself, and then the two vertical boundaries. One is the vertical line x is equal to a, and the other is the vertical line x is equal to b. So these are the four boundaries. The upper boundary is the curve y is equal to f of x. The lower boundary is the x-axis. The two vertical boundaries are x is equal to a and x is equal to b. So the area under this curve will be given by the process of integration. So how do we actually calculate this area? Remember, we are talking about this area that I am shading here. How do we calculate that area? Well, the actual process of integration can be thought of in this way. It is the integral, of course, from x is equal to a to x is equal to b. And what do we put here? The function of the upper curve. And what is the upper curve? The upper boundary of the area is f of x minus the lower curve. In this case, the lower boundary of the area is the x-axis itself. But it may not always be this way. For example, if you take a situation where this is a function f of x and this is another function g of x, and you want to find this area, then you can say that it is the integral from a to b, the upper curve of this region, which is f of x, minus the lower curve, which is this portion, g of x dx. And that would give you the area which is contained between f of x and g of x. That is the meaning of upper curve and lower curve. And this, it may not mean much to you when the lower curve is the x-axis itself, but in situations like I just described with a rough sketch, the upper curve may be one function and the lower curve another function of x. So it is important, and you will see the other reason why you have to be very clear about what the upper curve and what the lower curve are in other situations. So the upper curve in this diagram is the function y is equal to f of x, and the lower curve in this example is the x-axis itself, which is y is equal to 0. Since this is the situation in this particular picture, right, because the lower curve is the x-axis itself, which is y is equal to 0, this simplifies to upper curve, which is f of x, minus the lower curve, which is just 0 dx. And so this would become the specific case where the lower boundary of the region is the x-axis. Now this is an example where the lower boundary is not the x-axis. So let's see how it goes. So this region that we have here has this as the upper boundary, and it's called C2 here, and this as the lower boundary in blue color in the picture. So how do we find this region? Well, this area can be found using exactly this approach here. The integral from x is equal to a to x is equal to b. Now this is a, x is equal to a, and this is x is equal to b, where the upper curve may be given by f of x and the lower curve is given by g of x, and therefore that can be written as x goes from a to b, the upper curve f of x minus the lower curve g of x dx. That will give you the area bound between these two curves, the red curve and the blue curve. What about a situation like this? It's a little different, and you will see why. We are interested in finding out the region here. Let's apply the same approach that I have described to you earlier. In this particular region here, and I will highlight the boundaries in red so it's very clear. Well, x is going from a to b, that is obvious. Now the upper limit, the upper boundary of this curve, I will draw in a slightly different color, is that line. That is the upper boundary of the region, and the lower boundary of the region is here in yellow. So you can see that the upper boundary is the x-axis in this case, and the lower boundary is the function g of x. So how would we write this integral? This would be going from a to b. The upper boundary is the x-axis itself, which is y is equal to 0, because this line here is y is equal to 0, and this line here is y is equal to g of x. So the upper function minus the lower function, and that would give you the area. And this can be written as, it's negative, so you can swap the limits and say this is b to a g of x. That will give you the area that is indicated in this picture. So this concept will become further strengthened when you look at this question. So this is an interesting question, because not because you need, too many techniques of integration or some formula, but it reinforces the concept that I have been discussing these last few minutes. So take a look at this region here. Now this particular region enclosed by the blue and red functions can be seen as consisting of three separate regions. So this is one region, this is another, and this is the third. And you can think of it as the first, second, and third. Now, how do we write the total area bound by the blue and red curves, which is the sum of regions 1, 2, and 3? So this is area given as 1, area given as 2, plus area given as 3. How do we find this? Now, area that is marked 1 is the upper curve is the blue curve, and the blue curve here is y is equal to f of x, the blue function. That is the minus. The lower function in region 1 is the red curve, which is g of x. And what are the limits of integration? X is going from a to b, from a to b. That gives you the area of the first region. Now, area of the second region, in the second region, the upper function is the red function. You see, this is the red function, and that is g of x. And the lower function here is the blue function, which is f of x. And the limits of integration here are it going from b to c. And finally we come to the third part of our region, where the upper function is the blue function, which is f of x, and the lower function is the red function, g of x. And then the limits of integration are from c to d. And these three terms, a1, a2, and a3, when you add them, you get the total region, which is here, here, and here. And I want you to think about why we had to split it into three parts. Why did we not write it like this? We'll say it's going from x is equal to a to x is equal to d. So I will say a to d. And the upper function over here is f of x, and the lower function here is g of x. Why did I not write it like this? Integrate it from here to here in one shot. Why did I have to break it up into three different integrals or three different regions? Why am I worried about what is the upper curve and what is the lower curve in each part of the answer? Think about it for a second. The answer lies in this section over here. If you were to write that as f of x minus g of x, you will get the negative of the answer you are supposed to get. So which will therefore affect your final answer. So you have to be careful about how you consider the separate regions in a problem like this. Think about it for a second and you will get it. Find the region enclosed by these two functions. Now there is a straight line here. Y is equal to x plus 2 is a straight line, and this is looks like a parabola, and these two enclose a region, and we need to find the area of that region. And it is always useful to draw a rough sketch of a problem like this, because it helps you understand the two functions given here, what kind of a region is enclosed between them, what the limits of integration are, and so on. So let's start with a rough sketch. So let me draw, and you don't have to be very precise about it. You need to get a good idea and no more. It doesn't have to be a very precise drawing. So let's say these are our axes, these are our... Now y is equal to x plus 2 is very easy to draw. That's a straight line with a slope of 1, and the y-intercept is 2. So it is a line like that. So that is y is equal to x plus 2. So it can be a rough and crude diagram, but it will give you an idea of what we are doing here. Now let's talk about the parabola. Y is equal to x square plus x minus 2 can be easily factorized and written as x plus 2 and x minus 1. So it has two real roots. It's an upward parabola. It's a parabola like that. It is not a parabola like this. Why? Because the coefficient of x square is positive. So it's a parabola which looks like this. It's got two real roots, negative 2 and plus 1. So this, change that. So negative 2 is one root and plus 1 is the other root. And if you were to plot this parabola, again it's no more than a rough sketch. It will be like that. And this is y is equal to x square plus x minus 2. And now you get a very good idea what region is enclosed by these two functions. So it is this region here. It is that region. So how do we find the area of that region? Well, in this region, let's be very clear, what is the upper curve in that entire region? So the area is equal to the upper curve, which is x plus 2, minus the lower curve, which is x square plus x minus 2 dx. That's the area. But we have left out one important thing here. What are the limits of integration? Well, the limits of integration are, well, we can say x is equal to a here, and this point here, which should be x is equal to b. It should be fairly easy to find out these 2 points, because we are trying to find the points where this function and this function intersect. So you can substitute y is equal to x plus 2 in here and then solve for the two values of x and y. So let's do that over here, and I will use this color to, since we use y is equal to x plus 2, so we say x plus 2 is equal to x square plus x minus 2. So this goes, x square is equal to 4, x is equal to plus or minus 2. So we get the two values of x. These are the two values of x where the two functions intersect. So we now know the limits of integration. It is negative 2 to plus 2. Since we know everything we need to know to do this integration, we can go ahead and do the rest of it, and that should be fairly simple. And that comes to 32 divided by 3 units square. Remember, we are talking about area, so you need to express it as centimeter square or unit square. So this is how we got it. A rough sketch helps you visualize and make sure nothing is going wrong. It told you also, the rough sketch, what the upper curve in this region is and what the lower curve is. So we were able to set up this integral correctly. This is the upper curve and this is the lower curve, the y of the upper curve, and this is the y of the lower curve. We got that right, And then by solving, we got the limits of integration, -2 to +2. And then the rest of it is fairly easy. It gives you the area which is shaded in yellow. Now let's come to this. This is an interesting question, again designed to reinforce your conceptual understanding of this topic. Now we have a shaded region of this function, and it's going from x is equal to 1 here to x is equal to 7 over here, and it's got three parts. There is the first part, second part, and the third part. And the first question is, explain why the total shaded area is not equal to integral from 1 to 7 f of x dx. And this is similar to what we did a few minutes ago. Why is the area not equal to this? And then write an expression for the correct approach to finding the area of the shaded region. So that's the question. So if you apply the approach which says in every region we need to be aware of what is the upper curve and what is the lower curve, then for region 1 the area is 1 to 3, f of x is the upper curve, y is equal to 0 is the lower curve. So that's the area of the first part. The area of the second part is a2 is equal to integral. The upper curve is the x-axis, which is y is equal to 0, and the lower curve is f of x, and it's going from 3 to 5. And this can be rewritten as 5 to 3 f of x dx. And what about this region here, A3? A3 is integral from 5 to 7. The upper curve is f of x, and the lower curve is the x-axis, which is just 0. So adding A1, A2 and A3 will give you the actual area which is shaded. How is it different from the given expression? Well, it is because of this A2 here. You look at it, if you treat this region as just, and I'll clear the entire answer and get into another part of the explanation. I hope how we actually calculate the area is clear to you now. So I'll clear this portion, and then I'll say, if you were to calculate A2 as 3 to 5 f of x dx, then this would give you a negative value, because this region has the upper boundary as the x-axis and the lower boundary as f of x. Whereas here the upper boundary is f of x and the lower boundary is the x-axis. So if the actual area of this region is 5 square units, when you do this integration, you will end up with -5 square units. So that affects your answer. So instead of writing it like this, because this is wrong, if you write it, upper curve is y is equal to 0, lower curve is f of x dx from 3 to 5, then you will get the right answer, which is 5. And that is why in any given region, to be very clear about what the upper bound of the region is and what the lower bound of the region is very important. I hope this makes it clear the right way to find the area of region 2. Let's practice that concept a bit more with these questions. Write the integral expression for the following regions of the graphs, the orange area. and the blue area. Now these are two different areas, and we'll get two different expressions, but let's start with the orange area. So for orange, do I have an orange color? No, red is the closest to it, so I will stick to red. So the area of the orange region is this portion here, and for that portion, what is the upper boundary of the region? The upper boundary is this horizontal line, which is y is equal to 12. So the upper boundary is y is equal to 12. And what is the lower boundary of the orange region? It is this curve here, and that is y is equal to 3x square. And what are the limits of integration? The limits of integration well, x is going from x is equal to 0 to x is equal to 2. So we know everything we need to know to find the area of the orange region, and that would be a orange would be equal to integral 12 minus 3x square dx to 2, because we were very careful to identify the upper part of the region and the lower part of the region and then do it. How would the answer be different for the blue region? Well, let's do it by erasing this portion here. The upper boundary of the blue region is this curve, which is 3x square. The lower boundary of the blue region is the x-axis itself, which is y is equal to 0. And the limits of integration are the same as before, x is equal to 0 to x is equal to 2. So the expression for the blue region would be x going from 0 to 2, 3x square minus 0, so you can leave that out, dx. And you get different answers. I'm not completing the actual process of integration, but I'm setting up the expression so that you know exactly how to look at a region and determine how the area can be computed. A couple of other examples of this kind, and this is merely to reinforce the concept of how you can find the area between two functions. So let's do the orange and blue thing again. Let's do blue first. So area of the blue region is the upper curve here, and the lower curve is the x-axis. So it would be x into 6 minus x is the upper curve. 0, which is y is equal to 0, is the lower curve, dx from 0 to 6. And that will give you the area shaded in blue. What about the area shaded in orange? Well, the limits of integration are the same, 0 to 6. The upper boundary for the orange region is the horizontal line y is equal to 10, and the lower boundary for the orange area is this function here, which is x into 6 minus x. So by integrating it, and integrating that is not very difficult, you will get the area of the orange region. So this is how you can apply the principle of identifying the upper part of the region and the lower part of the region and using it in integration. Finally, this question. Write the integral expression for the blue area in this diagram. So we have this blue area here. So you can see that the upper boundary here is the line, this is the line y is equal to 1. That is the upper boundary of the region. The lower boundary of the region is the curve y is equal to x cube. So now it's quite easy to say 1, which is the upper boundary of the shaded region, minus x cube, which is the lower function dx, and it's going from x is equal to 0 here to x is equal to 1. And that, in fact, we can go ahead and do this. It becomes x minus x to the power of 4 by 4 between 0 and 1, and that is 1 minus 1 by 4 minus 0 by 4 . You can do it that way. So being aware of the upper part of the region and the lower part of the region is critical in getting the right answer, and a rough sketch is always helpful. So let's start calculating the areas of some of these shaded regions. Find the area of this shaded region. Now this is the shaded region here, and so the upper part of the upper boundary is the function y is equal to 2 root x, 2 divided by root x, and the lower boundary, pause the video here and tell me what the, or think about what the lower boundary is. The lower boundary is this line, the horizontal line, which is y is equal to 2. And we also have the limits of integration. First is x is equal to 0, and then the other boundary is x is equal to 1. So we have the limits of integration as well. So the area would be equal to, from 0 to 1, 2 divided by root x minus 2 dx. This can be rewritten as 0 to 1, 2 x to the power of negative half minus 2 dx. Square units. The process was exactly the same as before. Find the value of the integral and explain the significance of the answer. And this again is a highly concept oriented question. Let's get to it. So a rough sketch will help me make my point better. So if you think about the graph y is equal to x cubed, or you can plot it in a graphics calculator, it will look like this. Something like that. And these are rough sketches, of course, just to make my point. And we are integrating it between negative 4. So this is 4, and this is plus 4. So we are integrating it between x is equal to negative 4 and x is equal to plus 4. So we are talking about this region here. This is one part of the region, and this is another part of the region. So this is symmetrical. So these two regions are identical. It may not look identical in my rough sketch, but these two regions are identical. And I made a mistake here. It is not this region we are talking about, it's this region we are talking about. When you integrate it, you get this region. So that is the area under consideration. Now let's say that this region here, let's say that this region here is 5 square units, and this is also 5 units. But because the upper curve here is the x-axis and the lower curve here is the function y is equal to x cube, whereas in this portion the upper curve is y is equal to x cube and the lower curve is the x-axis. What happens is, if the actual area here is 5, when you integrate it from -4 to 0, a1 and a2, if you call a1 as 0, -4 to 0, y dx, you will end up with a negative answer for all the reasons we have discussed before. And therefore, you should be careful in identifying what the upper boundary of the region is and what the lower boundary of the region is. So if you actually integrate this, if you integrate, what do you get? Well, it's x to the power of 4 divided by 4 between -4 and 4, that is 4 to the power of 4 by 4 minus So how can this area be 0? Because I have clearly colored it in yellow. There is some region which is included here. But why does this process give me 0? That is because if this area is 5 and this area is 5, instead of giving me 5 plus 5, the answer is 10, this turns out to be -5 and this turns out to be +5. And therefore it becomes 0. Instead, we should not be doing integration like this. Instead, you should write it as a1 plus a2 is equal to -4 to 0. In a1, the upper part of the curve is the x-axis. The lower part of the curve is the function x cubed dx plus 0 to 4 x cubed. This will give you the right answer. So this is the significance of getting 0 when you integrate it like this. This is the right way to do it. Find the area of the region bounded by the x-axis and part of the curve y is equal to 6 plus x minus x square above the x-axis. Now clearly this is a inverted parabola and we need to find the area of the parabola which is above the x-axis. So a rough sketch once again will help. These are the y and x-axis, and let's factorize the given quadratic expression, and we can write it as negative x plus 3, or rather so the real roots are plus 3 and -2. So here, so it's a parabola which is something like this. Again, no more than a rough sketch, and that should do. And therefore the area we are considering is this area here. Now it's easy to find out what the limits of integration are. The limits of integration are from x is equal to -2 to x is equal to plus 3. The upper boundary in the region is the function y is equal to 6 plus x minus x square, and the lower boundary of the region is the x-axis here, and therefore that is y is equal to 0. So we can just write it like this, and this becomes 6x plus x squared by 2 minus x cubed by 3 between this should be 3 here, negative 2 to 3. On simplification, you get the answer 20.8 square units. Not particularly difficult. We will get to much harder questions later. We started with the easiest ones. I want you to feel very comfortable with the concept of area enclosed between two functions. Find the area of the region bounded by these two functions, the axis and this here. So it's important to understand what that is so that you have a visual understanding of what we are doing. Now, if you square both sides, you will end up with y square is equal to 9 minus x. Now, this is a parabola, but it's a parabola which has the axis of symmetry as a horizontal line, not a vertical line. So it's not a parabola like this, because the axis of symmetry in this parabola would be a vertical line. Instead, it's a parabola like this, with the axis of symmetry being a horizontal line. And you learn more about parabolas in the section called conic sections. But why am I telling you this? Because I'm going to draw a rough sketch, and that will help you visualize this better. So again, we have the axis here. Now, when you think about this function here, what happens when x is equal to 0? When x is equal to 0, we have y can be plus or minus 3. So when x is 0, this is a point and this is a point here. And when y is 0, x is equal to 9. Somewhere here, this is 9. So we have a parabola which is something like this. Something like that. Oops. And we need to find the area bounded by the axis and the curve y is equal to square root of 9 minus x. So if you go to that, we are talking about the axis, x and y axis, and let's say it is this region that we are talking about. So once you identify the region, and I'm coloring it so that it is visually quite clear what region we are talking about, then it's easy to set up the answer. The area is the limits of integration. X goes from 0 to 9. The upper part of the curve is y is equal to square root of 9 minus x. And the lower part of the curve is the x-axis itself. Therefore, it's just this. Now, how do we integrate this? Well, you can substitute 9 minus x is equal to t. Let's do that. Substitute 9 minus x is equal to t, and therefore dx is equal to negative dt. Having done that, we have to rewrite this integral in terms of t. So it becomes square root of t dt, but this is negative dt. Dx is equal to negative dt. What about the limits of integration? Here, when x is equal to 0, what is t? When x is equal to 0, t becomes 9. When x is equal to 9, the upper limit of the integration, t becomes 0. So this is how we write the limits of integration when x is replaced by t. And this can be rewritten by getting rid of the negative sign as square root of t dt from 0 to 9. I removed the negative sign and I swapped the limits of integration, and that becomes 2t 3 by 2 by 3 between 0 and 9. (18 square units). So we did it quite easily. Now I want to present to you an alternate approach, and I will draw a fresh diagram on the next slide and tell you how else we could have visualized the same problem. So let me do that here. This is x is equal to 9, and we have y is equal to 3, y is equal to negative 3, and that's our parabola. So let me try to draw that. Like I said, this can only be a rough sketch. Let me see if I can do a better job second time. Not much better. So that's it. So now this is, of course, the y-axis, the x-axis, and so on. So we are talking about this region. That has not changed. But how else could we have approached the same problem? That's what I'm going to discuss. Now, if you look at it from a different perspective, you can think of this as the lower boundary and this as the upper boundary. When you look at it from a sideways perspective, so this is the lower boundary, that is the upper boundary, and you can see that y is going from y is equal to 0 to y is equal to 3. So we can rewrite the integral in terms of y. So the area A is equal to integral of y is going from 0 to y is equal to 3. The upper boundary here is just x, because this is the upper boundary. This is the upper boundary, and at any point on the upper boundary, if I take this, what is the length there? That is just x. So it is x. And the lower boundary is the line x is equal to 0 itself, which is 0 dy. I'm rewriting the entire integral in terms of y. And this becomes 0 to 3. Now x can be written in terms of y as 9 minus y square dy, which is 9y minus y cube by 3 between 0 and 3. That is 9 into 3 minus 3 cube So you see how the same question could be approached in two different ways. One time we integrated with respect to x, and the other time we integrated with respect to y. It is the same region we are talking about. You can compare the first and second approaches. The region doesn't change, the answer obviously cannot change. But the first time we wrote the integral in terms of x, and x goes from 0 to 9. In the second time, we wrote the integral in terms of y, and y goes from 0 to 3, and we get the same answer. Next question is, find the area of the region bounded by y is equal to e to the power of x plus e to the power of negative x. The x-axis, x is equal to -1, and x is equal to 1. So there are multiple boundaries. There is this function, there is the x-axis, there is the vertical line here, x is equal to -1, and the vertical line x is equal to +1. So let's see what this shape looks like, because I prefer to draw a rough sketch every time to get an idea of what region we are talking about. So let's recall what e power x looks like. E power x looks like this, and this is 1. What about e power negative x? It's symmetrical to e power x, and the axis of symmetry is the y-axis. So e power negative x is this. This is e power negative x. So these are the two functions. If you add them up, what will they look like? Well, try and imagine what the sum of these two will look like. It will pass through the point y is equal to 2, and it will look something like this. You're adding the two functions, so it's e power x plus e power negative x. That's the rough sketch of the function y is equal to e power x plus e power negative x. Then what about the other boundaries? The x-axis is here. X is equal to negative 1 is here. X is equal to plus 1 is on this side. And what region are we talking about? We are talking about this region. As always, I like to color it so that it is visually quite clear what region we are talking about. This region. It has 4 boundaries. Y is equal to e power x plus e power negative x is the upper boundary. Y is equal to 0 is the lower boundary. X is equal to negative 1 is one vertical boundary. X is equal to plus 1 is the other vertical boundary. So the integral, which will give you the area, is x goes from negative 1 to plus 1. The upper curve is e power x plus e power negative x. The lower curve here is just the x-axis, which is y is equal to 0. So this is our integral. And this integral, it's quite easy to integrate it. So when I substitute these values, it becomes e minus 1 by e That's what we get. So this is 1 by e. This is 2e minus 2 by e. That is that's the answer. Fairly simple, and the diagram helps. So a quick summary. We did a few simple questions today, which allowed us to calculate the region between two functions. And I stressed for some time the importance of identifying what the upper boundary of the given region is. Because if you swap the upper and lower boundaries, then you get the negative of the answer you're supposed to get. So that was one important thing. So we did a few simple practice questions where we found the region bound by functions. And this is just an introduction and one specific area where integration can be calculated. Remember, there are other areas. We need to find the surface area and volume of three-dimensional objects. We need to apply integration in kinematics and in other situations. But those are topics for a later lecture. That will be all for today's lecture. Thank you for watching. I'll see you in the next class. Bye.